Good afternoon, everyone, and welcome to the third in our Masterclass series. And the theme today is how to improve efficiency and save money in food production.
Thank you all for taking the time today to join us, and hopefully we can convey some learnings that we have picked up over the years working across multiple sites and organizations.
Thank you very much, Crowley Carbon, and it's great to be here this afternoon. Please make a note of anything of interest and we can go through in the Q&A at the end of this session, or maybe after the webinar if you want to reach directly out to us. I'm sure you've heard of a lot of Industry 4 talk before, but I think talking about it will help put today's discussion in context. And with the adoption of any new technology or process, it's important to focus on the big picture. What we call Industry 4 technologies includes advanced robotics, AI, sensors, cloud computing, Internet of Things, data capture, data analytics, 3D printing, software as a service, and so on and so on. But it's really a technological movement that creates a framework for embedding these elements into an interoperable global value chain, or at the simplest level, a bunch of hardware, software, and cloud services that lets you see stuff you couldn't see before. Under the Industry 4 model, production can now take place in simulated environments and utilize digital tools to investigate production models, processes, and productive outputs, such as performance statistics. The networks of machinery in a smart factory can eventually become hyper-aware systems of highly flexible technology in their own right, responding rapidly, not just to human commands, but to their own perceptions and self-direction. The food industry is intrinsically built up of a combination of technology, machinery, people, and ingredients. All of these are variable. Effectively running a food manufacturing company means coping with change to a great extent. So therefore, being predictive and getting ahead of change is crucial, as is preparation and the managing of risks and challenges to seize those commercial opportunities. Most people start off by implementing an IIoT project, such as monitoring environmental conditions for the sourcing of food products. And being able to predict, you then have the ability to create metrics which enable you to optimize, streamline, and then calibrate after baselining your processes. This type of implementation brings competitive advantages. First movers expect to gain significant benefits from their more advanced digital capabilities and greater levels of investment. PwC in 2018 reports that companies which do invest in new technologies are more likely to be forecasting revenue gains of more than 30%, as well as cost reduction of more than 30% at the same time. In another survey from PwC in 2020, more than half of respondents expect their technology investments to yield a return within 2 years or less, given an investment of around 5% per annum of their annual revenue. However, Industry 4 initiatives come with health warnings. Firstly, in our experience in the food industry, we've seen many of the challenges facing manufacturers. Sites can vary enormously between the very small, with people making products manually, to the very large, with process areas across several buildings on multi-acre sites. Additionally, implementation of new products, new machines, and new lines can take time and requires a lot of planning. So it's important when undertaking smart factory projects to prepare the business with the right leadership, policies, and set of skills beforehand. Second, historically, IT and OT departments within manufacturing companies have functioned mostly independently. Operations kept the plant running smoothly, and IT managed business applications from the front office. For implementing an Industry 4 project, it's important that both teams communicate and align with each other. Third, getting data from machines can be difficult, and it's not easy constructing the right KPIs to finally transform them into actionable information. Industry 4 technologies transform data and transport it to places where people can use it, understand it, and make those management decisions. To overcome the challenges, you have to look at the people and the technology, and it's always people first. We help our customers develop and create strategies with a set of technology adoption stages, helping any manufacturing company to become smarter. Firstly, assessing. Evaluation of where you are now in terms of digital maturity and setting clear targets for the next 5 years, assessing your IIoT readiness and strategy. Secondly, understanding the impact. How the technology helps food and drink manufacturers decide on the best interventions. We help make sure that the technology adoption is the right one and the right level for each type of business. Thirdly, defining IT-OT convergence policies to enable digital manufacturing transformation, including enabling real-time decision-making through edge computing, eliminating unplanned downtime through predictive maintenance, and deploying wireless technology on the factory floor and ensuring cybersecurity. Fourthly, learning the value of data, how to build direct links between data, decision-making, and intelligent systems design. From the technology perspective, you need to work out how to integrate the three pillars of industry, which are industrial IoT, digital twins, cyber-physical systems. And companies can take advantage of all three, but you need to implement them successfully in the order shown, 1 to 5, so you can fully realise that automated future. Many companies have been dipping their toes in the water with proof of concepts for data analytics, and it's not easy to introduce control systems later on in the process. So you need to think of Industry 4 as almost as if it's a closed loop. We break down these stages into 5 steps for successful adoption: basic computerization, secure integration of OT and IT layers and all departments, connected machines, maybe with additional sensors for visibility, leading to a digital model of the factory to show what is happening at any given time, gathering the right data transparently and in quantities sufficient for meaningful analysis, which is the primary requirement for predictive maintenance. And finally, smart simulation of different future scenarios and identification of the most likely ones. This allows for accurate decision making and also the implementation of appropriate and timely measures. Thank you for your time, and I'm very much looking forward to the presentation from the Crowley team today.
Okay, so to jump into it, so just state the obvious, what Julian talked about, it was a little bit about how you do things and connect factories up and do Industry 4.0. Hopefully what we'll try and talk about is a little bit is why you would do this. And as I say, to state the obvious, obviously what everyone's interested in is driving continuous improvement in energy and sustainability and in process optimization as well. Big companies, all companies have big CSR targets, carbon neutral by whatever date it is. And they're really important, but also really important is driving continuous improvement on a day-to-day basis. And that can be hard. And we're going to talk today about some of the possible solutions to improving that workflow. So just to talk a little bit about, we talk all the time about 10x improvements in the tech world. So nobody would go back to renting a video and driving down to their local video shop and then forgetting to drop it back the next day and being fined for it and not having the movie that you want to see. Streaming and Netflix is a 10x or 100x improvement over that whole experience. We would never go back. But I suppose one of the things we believe or find is that really industrial energy efficiency and continuous improvement hasn't seen that 10x improvement probably over the last 30 years or so. Still factories are using PLCs and SCADAs and spreadsheets ultimately to drive continuous improvement. And they're all great, robust technologies, but really what we find with our customers is they're still using the same technologies, albeit an updated version of Excel and Siemens software, etc. So where is that 10x improvement and what does it mean? Well, one of the things it could mean is using the engineers, the smart engineers that we have in facilities to do more interesting and valuable work than just gathering data, walking around, reading meters with a clipboard, data that goes nowhere, or if it does go somewhere, it's just typed into a spreadsheet and it takes half the week to develop those spreadsheets and reports, and then nobody ever gets any value from them. So instead of doing that, could we do something better is the question. This is a reflection here of maybe the aspirational or theoretical continuous improvement process that people would like to have. So on the left-hand side, you have all the potential data sources. You've SCADA, BMS, lab information system, various meters, utilities in your boiler, air compressors, you've got operator logs, you've got supply chain systems, production information systems, ERPs, etc. Lots of data potentially. And theoretically, all of that data gets polled continuously, automatically gathered, sorted, cleaned up to a central point, which is, we call a collator. So that collator could be a person or software or both. And that collator is producing beautiful reports, CSR, energy, production reports, consolidated reports, and then experts to descend on those reports, and they pick through them and they see exactly what's happening, and they can see opportunities for improvement and possible problems coming up. So at that point, they say, okay, we want to fix the problems and we want to take the opportunity, so we need to take some action. So the two routes of action could be operational change, so changing a set point or cleaning a heat exchanger, or CapEx, so spend some money on a new heat exchanger or a new boiler or a new air compressor or whatever it is. But on this route, you got to do detailed design, you got to implement it. On this route, you got to take action, make the change, whatever that change is. And on both routes, you got to confirm the effect of that change. So CFOs give us money to invest. They want to make sure there is a return on it. And with energy efficiency, a lot of the time that can be difficult to prove the return is there because there's so many variables that can impact the process. And then you got to maintain that over years. So that's the aspirational. The theoretical or the reality of what we see more often and pretty much uniformly, it looks like this. So you might have a SCADA system, but it sits there in the control room. Nobody ever looks at the data on it except for the operators who look at one or two key variables. The lab information system is not connected to anything. There's meters, but some of them are wrong, and you don't have meters on the critical steam users or electrical users. The utilities just sit there doing their own thing. The boiler, nobody ever looks at it. Operator logs, nobody ever collects them or collates them. And the production, all the production information, which gives context to all of this, sits there in a silo and nobody looks at it. They're manually collected. If they are collected, they go to various different people in the organizations who produce various different reports. None of the reports correlate with each other. So if you get to this point, it's very difficult to see problems and opportunities because you're just not getting the right data. It's not correlated. You don't have all the right context. KPIs don't tell you everything because they don't take into account all the variables. And if you get to this point, there can be a lot of fear of change. So, changing that set point, well, we tried that years ago and quality didn't like it, so they pushed back, so we're not going to do it again. And if you go the CapEx route, well, then, there's not teams of engineers sitting around waiting to be employed on projects. And then if you get to this point here, it's very difficult to confirm the effect because you don't have the right meters, you don't have the data, and it's then, as a result, very difficult to sustain those changes over years. This is an example of that kind of reporting drudgery that we come across a lot of the time. So various different spreadsheets that are collated and people try and correlate them, estimated readings, couldn't paste up to regional, couldn't paste up to corporate. And the whole cycle takes 30 days. And by the time you get to here, you're looking in the rearview mirror, stuff that happened within shift is long happened previously beforehand. And your best engineers have spent hours and hours putting these reports together, and they're actually not analyzing the reports and the data as opposed to putting the reports together. Information overload as well. This is a typical SCADA screen from a plant that we would operate in that has 30 of these screens, hundreds of tags, thousands of tags, just information overload. So how do you grab this data but make sense of it so that it's actionable so you can take action from it? So how do we improve on that situation is the question. Using the technologies that Julian talked about and engaging the people, which is, we 100% agree with that as well. So step one is to start digging data out of dark corners. So we all know about air compressors down the other side of the plant that nobody's ever looked at. How do we dig data out of dark corners in the OT realm, put it together and use it to drive peak plant performance ultimately? So this is where we are on the workflow, just to remind ourselves. So we're at this point here. We want to dig that data out of those various sources and start putting it together automatically.
So there's a whole host of data available out in the field that we sometimes find are isolated. And to bring it back to Alan's point around the importance of a central collator, it is vital that all of this data that is available to you in your organization is collected at a central point. And we've all heard the buzzwords like Industry 4.0, Internet of Things, but simply put, they can be described as a central collator. So you may have assets out in the field like standalone controllers on boilers, compressed air systems, standalone PLCs, flow meters, energy meters, and so on, all of which have highly useful data. And these data points can be easily harnessed, and there's always a solution for every type out there, whether it's 25-year plus old technology or modern technology. Solutions can include hardwired or wireless infrastructure and encompass all different types of communication protocols like Modbus, OPC, BACnet, and many, many more. And I suppose the important thing here is putting yourself in a position to take advantage of all of this data that you have available to you.
this is a situation we worked on a year or so ago, where we're working in a plant and it had a very nice cooling tower with a very nice control system on it, but it was out the back. The PLC sat in the shed. Nobody ever looked at it. Lots of instrumentation potentially, but it wasn't connected to anything. And when we connected it up and ran it through our performance algorithms, we saw that the cooling tower, the water coming out of it was too hot for the load on the cooling tower and for the ambient conditions pertaining on the particular day. And the cooling water was being used to drive vacuum in the factory. So the colder, the better. The colder, the deeper the vacuum, the less steam consumption would be in the factory. So when we hooked it up, ran it through our algorithms, figured out it was not meeting performance, we went to investigate it. And as it turned out, it was just a simple balancing issue on the cooling tower. So we rebalanced the flow over the top of the tower. That was stopping short circuiting happening. And we dropped the water temperature coming out by about 4 degrees. So about 2 days work, about £1,000 labor. And the impact was pretty radical or stark. So over this period of time, you can see the cooling water temperature here dropped by about 4 degrees. The vacuum improved significantly. And as a result, the steam consumption on this distillation process dropped from about 1.5 tons to about 1 ton over 3 days or so. And on that particular piece of equipment, it was about half a ton, but over the whole factory with similar pieces of equipment, it was about 2.5 ton saving. So it worked out at about £250,000 a year savings for about £1,000 labor, and obviously the cost of connecting up the cooling tower. So it can be quite powerful pulling in these silos into an overall model to see how they're interacting with the overall plant and judge their performance. So step 2 is to make sense of this new data. So you've got all this OT stuff hooked up, all the oil compressors, cooling towers, production information coming in through the cloud. You got to make sense of it. And food and drink plants are complex and getting more complex. You know, there's more SKUs all the time. Plants are up and down all the time. The market is dictating how the plants run. So they're getting more variable and more complex. So where we are in the process is here. So we've gathered the data and now we're pulling it together to make sense of it. So just to say, I mean, we're moving hopefully from a position of data scarcity where there was no data to hopefully not data abundance, which is like drinking from a fire hose. So you can't make sense of the data to data clarity. So seeing exactly what's happening in the plant and how it's performing versus its production rate or the weather or product mix. So one way we do this, and Julian alluded to it as well, so there's a lot of different terminology and buzzwords for this kind of process. There's digital twins, there's hybrid models, there's hybrid KPIs. But in essence, what they are is trying to distill down very complex systems into live targets for how the plant is running. So the process of doing that is taking the design and operating data, so P&IDs, drawings, etc., building a detailed process model for whatever the process is, and that can be in Excel or it can be using other tools, more complicated tools like Aspen Custom Modeler, and then developing what's called a reduced order model, so boiling it down and getting correlations from the model, and then putting those models into a live data stream. So you're pulling the data out of the plant, feeding it into the model, and then getting live targets for how the plant should operate based on the particular conditions on that day. So what that looks like in reality is something like this. So you've got, in this case here, a very complicated distillation process. And ironically, we are distilling that down into a model. And we've got a live platform here, which is basically running the model, and it's being fed with the live data coming in from the plant, from the SCADA system, so pressures, temperatures, flow rates, etc. And it's saying for the conditions on the day, this is the optimal steam use. But you can see here, the actual steam use was this. So there's a gap between them of about a ton of steam. So about €200,000 a year in this particular plant. So the possible saving is this. So over a period of time, the operators worked to optimize the plant, optimize the temperatures and vacuums, and you can see the results here. So they're actually tracking the optimal steam consumption here. So that is basically their new target line. So they don't have KPIs, which you don't take into account the weather and the cooling water temperature and vacuum and everything else. They're actually running the plant on the optimum. And then you can distill that further across the enterprise. So in this case here, it was an enterprise with multiple sites. And this is a distilled down report, which is taken into account. On the right-hand side, you can see The size of the bubble indicates the energy spend of the site, and the color of the bubble indicates how it's performing versus the model. So in this case here, they're all doing pretty well, except for there's one red site which is doing not so good against the model, the predictive model, and that's something to look at, albeit it's only a small site. So the ones to look at really are the bigger sites which are drifting slightly. So step 3, having all this great information and reports obviously doesn't automatically turn into savings. So how do we get the best eyes and the brains on that data, on the reports at the right time to drive CI? That's where we are in the process. So we're steadily moving around. What we're saying here is, so you get a deviation, it pops up over the optimal steam use line. You know there's something happening in the plant. Maybe vacuum is drifting, or there's a heat exchanger that's been failed. Then what do you do?
And look, yeah, and just to follow on from that, from what Alan just said, a good simple example of this from a site that we were recently on. We worked with the site team. We collated all the data from a process SCADA system and a refrigeration system that were siloed apart historically. But within 3 hours of analyzing this data, the refrigeration SME was able to flag certain inefficiencies around an 85-degree CIP system being used to clean out the primary side of a heat exchanger when it got fouled. So for years, the site had been bypassing that chilled glycol circuit had not been bypassing that chilled glycol circuit away from the hex during the process, which happened a couple of times a day and led to chillers being under tremendous pressure to bring down the temperatures of that circuit. So that simple oversight led to around 25,000 of wasted energy a year, all because the data from the two systems were separated and were not being analyzed in the same location together.
So the other thing to say here is it's important to have a tool that allows you to bring in that expertise in a frictionless way. So this is an example of a Kanban dashboard. So you can see here, so alerts pop up, you exceeded the air compressor consumption for whatever reason, it's over the predicted model. So the model is taking into account production and the other kind of variables that impact it. So then you can pull in experts here. So you can see, you can pull in these experts, but also when they dive into it, they can get all the data to hand. So in this case here, they can get all the backup data for the air compressor. So spec sheets, they just click on that. Everything's to hand, so they can read themselves into this problem or opportunity really, really quickly. And also all the performance data is to hand. So you can see here, these are performance graphs for the air compressor. So kilowatt hours per meter cubed coming out of it. And you can very quickly spot what the opportunity is. So they can either take that opportunity or fix that problem as quickly as possible. So step 4 is, as we talked about, you can do all that stuff really well, and there still be some resistance, whether it's not having resources, or we tried this in the past and it didn't work, or different stakeholders in the company like quality or wherever it is not wanting to change. So there has to be a system around developing a bias towards action. You've done all the hard work of gathering the data, you've built the models, you've brought the experts in, now we got to make the change. Before any change is made, obviously it's very important that stakeholders are brought along, so all the various stakeholders in the plant, but everyone is clear on possible unintended consequences. So is there an impact downstream? And as we said before, plants are complex. So being able to understand the plant fully really means that you've got to get into granular detail. And the way we would do this typically is, build PFDs for the plant, and hopefully the plant has PIDs and PFDs existing, but a lot of older plants don't, or the plant has changed so much that the PIDs aren't updated and they're completely different. So get a fundamental understanding, build PFDs, build a process model. So either using Excel or something complicated like Aspen Custom Modeler if it's a complex process, and then getting a full mass energy balance. So this is an example from a dairy plant where we sat down with the customer, we built this mass and energy balance over a period of a couple of weeks to get a fundamental understanding of what was going where and what heat was being exchanged with whatever streams. And it was a really powerful exercise. The customer actually got a fundamental understanding of their plant, which they hadn't up to that time. But it allows you then to understand possible interactions, unintended consequences, and be able to foresee them and predict them. And then in that case, to make the change, you can build process trials. So with quality, you can build process trials like, making sure you're doing the right analysis, the lab analysis, the quality analysis, that the frequency of doing that analysis is agreed and checked. You're doing it as frequently as you can. You're monitoring certain parameters to make sure that there's no knock-on effects downstream. So you're doing it in a structured, controlled fashion, using the mass and energy balance, using the data coming from the plants that you've already gathered, so you can see everything, and you can see everything downstream, and you can bring on board the quality people if required.
Okay, so this is another good example of leveraging data that was siloed on its own, collating it into a central point that relevant SMEs could access easily, and optimizing this system to achieve 38,000 in savings. If you want to go to the next slide, Al. So site ran this particular refrigeration system in a certain way because they always felt that the cooling tower could not handle the cooling load required on its own. So they always ran 2 mechanical chillers 100% of the time alongside it. The system was properly analyzed, and a model generated that indicated that at certain times, depending on the wet bulb temperature, the cooling tower was more than capable of adequately handling the load. And by running the mechanical chillers when not needed, this was running up a 38K bill of wasted energy, essentially. So taking the time to analyze, design, and measure the impacts of changes made, this will increase your confidence and the confidence of the people you are reporting into, and to make more changes.
So step 5, the final step, is making sure all that value and change is sustained. And as we say, low-hanging fruit tends to grow back. Low-hanging fruit is great, but it does tend to grow back, as does high-hanging fruit. i.e., if you've made the change for the heat exchanger, you've put a heat recovery loop in to recover some heat from some process stream, it can get fouled and bypass, and then it's not doing anything. The other way of looking at this is, why is it that your CFO hates energy efficiency investments? Energy efficiency is more difficult than solar, for example. Just putting solar panels on the roof, it's pretty non-intrusive. And once the sun shines, you get the savings. Whereas energy efficiency, you tend to be able to have to take the plant apart, if it's a refrigeration plant, put it back together in a more optimum way, and that's intrusive and it takes a little bit of time. And then the savings that accrue from that can be dependent on weather, it can be dependent on production, whatever it is. So how do you make sure that low-hanging fruit does not grow back? So how do you confirm the effect in the first place, but then sustain it over the long term?
So this shows the importance of continually measuring and reporting on changes made, not only to positively report the changes, but to also ensure you sustain those savings. That's the important thing here, is once you achieve those savings, you got to ensure that you sustain them. So you can see the trend graph in the bottom left-hand corner there. It shows the modeled chiller consumption of how it would be running if changes were not made. And you can see that in red, versus the trend of the actual consumption when the improvements was made, and the clear difference between how it was consuming energy to how it is consuming energy now. So being able to close that gap via building good working models is really essential. So to ensure you sustain these positive changes, you can set up watchers or alerts that will alert or alarm you if multiple conditions or thresholds are met. And this allows you to keep on top of any deviations and ensures that you sustain those savings long into the future, and sustain the confidence of the relevant stakeholders.
Just to talk about some numbers and some kind of low-hanging fruit that we've seen in our experience, and opportunities that might be available. So utilities generally, starting here, are pretty neglected. The boiler man that used to be there all the time retired 5 years ago. Nobody really understands refrigeration anymore. So utilities are a big opportunity, and they consume most of your energy. So they really should be looked after. And we find typically about 55% of boilers and cooling towers are not connected to a central point, whether it's a central SCADA or some other system. And that's an opportunity from an efficiency point of view. 50% of critical steam users are typically metered, and that's a big opportunity. If they're consuming most of your steam, you should know what's happening with that user. And then if you have a SCADA, typically we find 20 to 40% of the control loops that are in the SCADA currently are in manual, or they're poorly tuned. You know, the valves are oscillating and banging. You don't have good process control, and they're chewing through more steam than they have to. As we mentioned, there's a huge opportunity cost in tying up resources in data collection and reporting, manual data collection and reporting. You know, there's probably a 3x opportunity cost for taking that time that they are using with those drudgery reports, developing those reports and generating them, to actually getting to do engineering work, looking at the data, looking for opportunities. Typically 80% of plants don't have detailed mass energy balances. So the fundamental understanding of what's going on in the plant is not there, and therefore the interactions and the opportunities. And 90% of plants we find are using static KPIs, and they're better than nothing, you know, just dividing the kilowatt hours by over the production tons or units or whatever it is. But there's a real opportunity understanding what exactly how the plant is performing, and having a target line to drive towards, and having the operators drive towards. All that adds up to about 100 to 500,000 euros a year, depending on the size of the plant, but typically it's in that range for not a lot of investors. In summary, where we think we can go with industry is on the right-hand side. So clear motorways, safe motorways, you know, driving towards big CSR targets, but also daily continuous improvement. And not on the left-hand side, you know, dark, unlit roads, which are obviously fraught. And the tools are available, the methodologies are available to be on the right-hand side as opposed to the left.
So we did get a couple of questions there during, that was great, guys, by the way, thanks. Dara, I think you did the Mythbuster slide, and somebody said, this sounds like a good process, but time to do this is not there, and getting outside expertise in won't be an option.
Okay. It's more of a statement than a question, but
yeah, well, just I've a view on that. My view on that is that a lot of the time companies don't actually calculate the cost of the opportunity cost of having people do, you know, reporting and collecting information. So where we do this a lot with customers is actually just map out all those gaps in that process and put cost and time against each of those gaps. And when you add it up, it's a huge amount of money, and it really makes the case for doing something better, whether that's getting external information or putting systems in place or going towards Industry 4.0 or whatever it is. The value is definitely there to be liberated.
Okay, great. So another one here, very good presentation. Thanks. How do you find end user perspective in F&B around cybersecurity in relation to other industries? It's a high priority.
Probably one for you, Julian.
That's possibly one for me, isn't it? Perspectives in food and bev. I mean, traditionally, food and bev is often seen. Food and bev is one of the biggest manufacturing industries, but they tend to also have the biggest sites, the most legacy machinery, and a lot of the different problems. So food and bev is particularly important, I think, in the light of what's happened with COVID as well in the last 12 months or so. I always sort of bring Germany into the picture in here, but as food and bev is classed in Germany, and particularly in cybersecurity matters, as a critical national infrastructure. And I think the same things happened with a lot of our customers during COVID, where they've had letters from the government saying, you know, you've got to keep the lights on, fellas. We're classifying what you're doing as critical national infrastructure now. So I think boards are beginning to understand the need to start thinking about investing in security. And one of the great things about things like saving, you know, being able to save money with energy consumption is you can start using some of those savings and some of those discussions with those CFOs to start saying, okay, now I can prove that we can be more efficient in this part of our process area. We can use some of the savings or some of those CapEx budgets now to start securing some of the assets that we now know need to be more secure.
A couple more questions here. So how do you drive selling the benefits of improvements through sometimes negative directors?
Presume that's related to, you know, how do you justify the value of doing this generally? And we have we've a very granular, I suppose, process that we go through with customers. So I mean, there's different layers of value. So there's obviously potential energy savings that come out of this. There's time and productivity improvements. There's potential process improvements. So it's a kind of a detailed exercise that we would go through the customer. It's a template that we would work through them. And basically it's going through that workflow that we talked about. So the gathering the data, the sorting it, the collating it, finding out what the frictions are at each point and putting some quantification on that, you know. So if there is people spending 2 hours a day, you know, walking around the plant, taking readings, you know, there's a value to that and them not doing that. If they're spending half their week manipulating spreadsheets, you know, if we can avoid that, there's a value to that. And then we have kind of proven rules of thumb from being able to, you know, deliver energy savings, basically.
What Alan's saying is excellent. One of the things that I mentioned my cybersecurity background originally, one of the things that it was always seen as a cost center. So a trick I learned from one of my customers in food and bev many years ago was, it's when you're selling the benefits of the improvements to the director, don't call it something that's seen as a cost center already. Yeah. So with something like cybersecurity, we were saying, look, this is actually a loss prevention project here. We're looking to save money on loss from all different kinds of processes and angles here. And then wrapping it up and presenting it in that way was quite an effective way of offsetting some of those negative, you know, those negative directors and negative objections.
So I don't know who wants to jump in. Are you available to implement the software and pay for it from generated savings? Oh, that's a good one. Alan Keogh, maybe?
Yeah, it's certainly a discussion we can have, yeah.
To the team, have a go. It appears that there is a lot to be done in general. Is there always an obvious first step in starting an improvement journey? That's a good one.
For us, it's always visibility. It's understanding actually what you've got that's going on out there. It's always the first step on the journey to be able to answer those questions, because if you don't know what you've got, then you don't know what the effect of changing something will be. And we're getting asked a lot about that these days. It's becoming more, you know, more and more of a problem as more folks. And I think, as Alan said, you know, the boiler guy retires. The engineering teams have fewer staff, you know, budgets for keeping the lights on. You know, you've got to have that visibility on the systems and processes that you're running, even more so now. So.
Okay, so I have brought in outside energy expertise in the past and have had more bad experiences than good. What do you say to that?
And it's good to set out goals at the very start. You know, set certain expectations about what you're looking for and what, you know, those experts can deliver on, and just make sure everyone's aligned from the very start. Maybe, you know, implement a small POV so whoever you get in doesn't end up wasting your time if they don't bring you what you're looking for. That's what I would advise on that.
Yeah, and I would add to that to say, you know, back to stakeholders. You know, if people come in with size 12s and, you know, say they're gonna take half the energy consumption off a plant, and, you know, annoy people who've been running the plant for 10 years, you know, that engagement isn't going to be there. So as Dara said, you know, starting small, getting some quick wins, having expectations aligned, which is why we do the gap analysis. You know, it's a very powerful tool for seeing the gaps first off, but also that the expectations are aligned, that, you know, in the first 3 months, look, you know, we're not going to boil the ocean. You know, we're gonna get these wins for you, these smaller wins, and they're going to build confidence, and those stakeholders in quality or maintenance or wherever they are going to see those wins, and then we go from there, or not, as the case may be.
Julian, one last one for you.
Yeah.
And it says, are people really spending money on IoT initiatives with COVID-19?
I think, yeah, absolutely. I mean, last year was certainly, with talking with customers, was about keeping the lights on and reducing, you know, the number of products that they were making, keeping things simple. And what we've seen in the last 6 months, that it's gone beyond that. Now, IoT is not just a proof of concept or a proof of value for some customers. It's going into actual production now. So where we're seeing enterprises reduce their spend on IT, because they don't need offices anymore. Stuff's moving out their data centers into cloud all the time, into public cloud. So it's kind of freeing up some of those budgets to invest in the business and the things that actually make customers money. So this is what we suspect is now, driving those initiatives and then into production. So absolutely, and I think some of the understanding around some of the OpEx capabilities really, and using the cloud to fund those projects are now filtering through, to throughout the businesses basically, because folks have to become have had to become more agile and increase the speed of adoption of some of those technologies and services as well. So it's absolutely what we're seeing out there right now.
Great. Julian, Alan, Dara, thank you very much. This has been great this afternoon. Thanks. And thank you everybody for joining.